So, in this lab, so for the Rotational Inertia Lab, so here's our prelude to the Rotational Inertia Lab. So here you have the rotating table. So here there's the drum that comes out through the center, which is part of the harness, which then is attached to the mass, which is then going to rotate. So wrapped around the drum there is a string. That string then is going to be pulled by this hanging mass, which is going to cause it to accelerate. So ultimately this portion here will then accelerate in this direction. This is going to then accelerate downward, which means that here we're going to choose our positive y direction to be in this direction. Now, for this lab, the first thing you would have to do then is determine how much friction is actually within this harness. Now, to do that, basically you're going to replace M hanging here with M star. So typically the first thing you would have to do then is hang a whole bunch of different varying masses off of this thing to try to figure out how much mass do I have to apply into here to cause this thing to actually rotate at a constant velocity, meaning that there is zero angular or zero linear acceleration on this thing. Now, the way we do that is typically we're going to put flags here, so that the flag's drawn here, but imagine here I have a flag here, also put a flag here, and then over top of this we're going to put basically a photo gate. So what will happen is every time these flags go through the photo gate, it'll then measure the fact that this flag has a width of 2 centimeters, and then it times the amount of time that it takes for it to go through the 2 centimeters, and then from there it's going to extract the acceleration. And again, what you're looking for is that you have constant angular velocity when you have m star, and then when you place mh, this thing then is going to accelerate, and then we're going to extract 10 different accelerations for the 10 different objects. So the 2 different objects are going to be the ring and also the disk. So in this lab, the only thing you have to calculate is the moment of inertia. Now, the moment of inertia will depend on the geometry of this thing. So this big radius, which is the radius of the disk itself, or the ring, little r here, which is the radius of this drum, as well as the masses that you're hanging, and the mass of this object as well. So here we're just going to calculate what exactly is this this moment of inertia. Now, to find the moment of inertia, what we know is that, according to Newton's second law, that the sum of the torques acting on the object, in this case we're taking the sum of the torques about the center of mass, must be equal to the moment of inertia times then the angular acceleration. Now, in this case, what's causing the torque is this tension here. This tension then is acting tangential to the drum, which means that it's on a 90-degree angle. So remember that torque goes as the distance, at least the magnitude of the distance, times the magnitude of the force times sine of the angle between the two. But in this case, if the angle is 90 degrees, then sine of 90 is simply 1. So we don't have to worry about that. So this is going to cause it to rotate then in the counterclockwise direction, which will be a positive torque. But since we have a frictional torque, hence we're looking for m star here, we're then also going to have to subtract off that frictional torque because it's going to act in the opposite direction, which means it would be a clockwise rotation in this case. So here we're going to have the torque then by the tension minus then the torque by the friction, which is equal to the moment of inertia times the angular acceleration. Now, the torque by the tension is simply going to be the distance at which this is acting, which is then little r, times then the tension, again times sine of 90, but sine of 90 is simply equal to 1, minus then, now in this case we're going to model this friction as simply, what, the weight at which this is thing pulling down, and again since it's moving at constant speed, that's then just going to be the distance, again it's acting, which also is little r, times then m star times g then is equal to the moment of inertia times the angular acceleration. Now, from here, we can then say the sum of the forces in our y direction are equal to m hanging times a. And again, since we're choosing positive y direction downward, so this is m hanging times g minus the tension is equal to m hanging times a. So solving this tells me then that the tension is equal to m hanging g minus m hanging a. So we're going to plug that guy into here. So this is going to become r times m hanging g minus then m hanging a minus m star g is all equal to the moment of inertia times the angular acceleration. And we'll talk about A here in just a second. So, good. Now from here, what do we have to be careful of? Now here, what we're measuring is the acceleration of this portion here due to the flags, where this linear acceleration is actually acting at the distance of the full radius, so capital R. However, this acceleration that's generated here actually is the acceleration which is acting on the little drum here, which is not exactly the same as this acceleration here. So even though we're plotting and we're extracting what that acceleration is, we have to be a little bit careful in the fact that that acceleration is not the same as this acceleration. So let's call this A small, and then this one, which is acting on this guy, so this portion here is accelerating in this direction, which is then A large. Good. Now, so just to write that here. So effectively what we'll end up having to do is what? Rewrite A small then in terms of A large. But we'll do that in just a second. So good. So here, what we know is that what? The angular acceleration is related to this large acceleration by the fact that, remember that angular acceleration is related to tangential acceleration by simply the radius. So here, I could rewrite alpha in terms of A large. So this is going to be the same thing as moment of inertia times A large, all divided by the overall radius. Good, so let's solve this for the moment of inertia. So this becomes little r times big R times m hanging minus m star, all times g minus m hanging times A small, all divided by nothing, or yeah, A large is equal to the moment of inertia. Now, finally, again, what we have to do is we have to relate A small to then A large, but note that what? The A small, which is acting here, is also related to the angular acceleration alpha, also by its radius. So A small is the same thing then as the angular acceleration times the little radius, which means then that's what? If we solve this one for angular acceleration, solve this one for angular acceleration, those two angular accelerations have to be the same. So we'll simply relate those two to each other. So from here, we can then say that what? Angular acceleration is equal to A large divided by the large radius. Well, that's also equal to A small divided by the small radius. Which means that A small, according to this, is simply the same thing as the little radius divided by the big radius, all times then A large. So if I replace that in here, so we finally can write this as what? Little r, which is the radius of the drum, times big R, which is the radius of the object, times then the difference between m hanging and m star, times g, minus m hanging, times then, according to this, this is going to be little r times A large divided by big R, all divided by A large, is equal to the moment of inertia. So, again, all you're going to be doing is, at least what's done for you, is that we're giving all these parameters. You're given the radius of the drum, you're giving the outer radius of the object itself, you're given m hanging, you're given m star. So from here you have 10 different A larges. So you have a different A large here and here for all different trials. So again, you have 10 different trials for all the different masses. So in that case, you're going to calculate this moment of inertia 10 times for each one of those different accelerations. From there, calculate its average, also its standard deviation. Then calculate the theoretical values. Those theoretical values can be found on page 2 of the lab manual. From there, you're going to do the discrepancies, both relative and absolute discrepancies, between this average value as well as those theoretical values. From there, you can either use that same spreadsheet that I gave you or use a new spreadsheet, whatever you want to do. But just fill out those and then turn those in. Like I said, the lab manual asks you to do the angular acceleration as well as the net torque. But in this case, I'm not going to worry about it because, again, the net torque is just simply going to be the moment of inertia times the angular acceleration. But again, I'm not going to require those. The only thing I want you to do is actually calculate what is that moment of inertia 10 times.